So what are we talking about today? This is pulled from our quantum training program. So the quantum program, the purpose of that was to create trainings that, while we will talk about how you do it in Q-SYS, the quantum training is just basic AV training, right? Things that you need as a technician to go along. So I nicked this out of there. So because gain structure and AEC, having done some field support, I've never worked on this. People like to do that answer our phones, all day long and deal with that. But and God bless them for deal with that. That takes a special breed of people. I mean, I'm not a remote. I don't like to have to remotely help people. But 9 times out of 10, when I help somebody out with an AEC problem or just an audio type issue, it usually has something to do with they didn't set gain structure right, or they didn't understand the principles of AEC. So we're going to go through kind of a run through on both of those. So, all right, I'm going to start out first with essentially this is a troubleshooting guide. So when you get the PDF version of this, you can kind of walk through it. We also have what I call the placemat, which I'll send out, which you can print off in 11 by 17, fold it up, put it in your, carry it around with you. And it kind of walks through all the steps of how to set up proper gain structure, kind of like a quick setup guide instead of having this long, lengthy PDF of 60 pages. So it's important to set gain structure as a basis for all audio in the system. And just remember, garbage in is garbage out. Like if I bring a horrible signal in and I can't process it in the input phases of my design and get that whatever bad characteristics there are out of it, then I'm going to end up just transferring those same bad things out. There's no magic fix for having bad audio coming in there. Now, there's some things that we can do to manipulate that audio, and we'll get to that. All right, so I think it's important first, proper gain structure is a key component. It gets you for setting the performance of a Q-SYS system or any DSP that you're dealing with, right? So bad input levels are improper dynamic processing. So things that you're going to do with compressors or limiters or things like that will affect the whole signal chain. So you want to make sure that you're starting off on the right foot. Now, we have to start first, and I love the quantum series about this because usually, there's an overhead review, and then we talk about what's the new terms and language that we're going to learn. So first off, the noise floor, right? So it's important to know the noise floor is associated with whatever circuit is being used, right? And so that's going to be, if I have just an open analog input on a core, I'm going to, it's whatever noise that might be picking up. Like by default, it might be -81, but if I plug a microphone into that, it might be -50, -43, or something like that. So that's going to vary depending on what you do there. So. In the language of audio, it's important to understand dBu, which is what's referenced on this chart. So you'll see there, we're talking about dBu, -81 dBu. The nominal level, the dynamic range is -81 is the bottom, and +24 dBu is actually the clipping point, right? So, and that's how we reference that. It's a dB referenced against a 0.775 volt standard, right? +24 dBu is a clipping point for all professional audio devices. And you can't pass a signal that's bigger than the power supply of the circuit that you're feeding, right? So you have the noise floor and you have the dynamic range there. And that's just the dynamic range is whatever the noise floor is. If it's a super quiet input and it's at -81, and we have +24 is where we clip, then we'd say you have 105 dB of dynamic range. Clipping is when you have an input voltage that's higher than the maximum voltage that the power supply is going to allow, or if the income signal sine wave is larger than the input device can process. Excessive sine wave then gets clipped down, so you kind of clip the tops off of that. Is where that term comes from there. It's going to, when it gets clipped down, you may be overdriving the inputs, you may cause some distortion. Every analog device has some sort of noise associated with it, right? Even if it's just an open input on the back of a processor in a rack. Now, you could mess with that and like plug a wire in and use it like an antenna, and you could see, if you experimented with it, how that level would go up. example for clipping, max noise floor, like I said, is negative 81. Dynamic range is 105 because that's the difference in there. Lot on that one to cover. But headroom. So headroom in general, it takes about 10 dB to increase the SPL to be perceived as twice as loud, right? We like our audio signal then to have about 20 dB of headroom. So you got to think this is for speech, this is for music, this is for whatever we're doing, right? So that's when we talk about headroom, you'll see on the chart that when you set inputs coming into a mixer or coming into a system, you're looking for +4 dBu. I don't know if anyone's familiar with old analog desks and analog mixing consoles, where they had big VU meters. Those were dBu meters. And actually +4, a lot of people think 0 dB, but +4, just a little off of that, is where a nominal level where you want to set all your inputs to. So the difference between that nominal level and the clipping point is 24 dBu, or is 20 dB, right? And then signal to noise ratio, this is going to be the difference between the noise floor and where the nominal level is. So in dBu, this is going to be, in this example here, negative 81 to +4 is 85. So you're going to end up there. So now some nominal level standards. Professional line level is going to be at a +4 dBu nominal. Consumer line level is going to be about negative 7.78 dBu or negative 10 dBV. And then microphone level could be anywhere, but typical non-dynamic microphones are going to be about negative 60 dBV or negative 57 dBu roughly. So there is really no standard for that. Some microphone levels can be different. And then when you get in condenser mics that have phantom power, those could be, need negative 30. They could be all over the map. So, but just know that. But that nominal level is the sweet spot that allows for adequate headroom and maintains the best signal noise ratio. So we want to stay with professional whenever possible. And we'll talk about on the output side what we need to do to make that work for downstream devices if we're not going into there. So preamplifier circuit. So the preamp has analog circuitry where the gain is added to the signal to match a level that we want, right? So if I've got an upstream device that's coming into my design, then, a microphone is a good example, but it could be anything. I need to be able to raise that gain of the device so that when I go into the analog to digital converter, I'm presenting it a good, nice, clean signal. And then that signal will go into the digital domain. Now, to understand the Q-SYS gain structure, we have to understand what happens when we go from analog to digital. Okay, and we're one of the unique DSPs, and I haven't looked at a lot of our competitors lately, but I do know that we're one of the few that our input meters and a lot of meters throughout the design are in DBFS. So DBFS is dB full scale, and the reason that changes once we come into an input, once we go through the analog to digital converter, it's dBu before that, and it's DBFS after that. Because in the digital domain, what we have, digital audio systems sample the analog waveform. That sample value is scaled in comparison to the voltage, and it requires us, now we're talking about full scale, right? So 0 dB full scale is actually the clipping point. So that's the maximum. So it makes the math easy. That means that your nominal is negative 20. And then whatever below negative 20 dB full scale is that. Now, I say this because it's important. When I first started using Q-SYS as a DSP and things like that, I was used to other brands where I would, I bring all my input gains into about 0, right, on the meters. And when I did that, I'm like, man, I've never added 58 dB to this, table mic or whatever to get it there. And then I realized that I had all my mics almost at clipping point because I didn't realize it was in dB full scale. So if you walk away from this training with anything, it's understand that our inputs are all going to be, once they go through the analog to digital converter, all our meters on the inputs there are dB full scale. So you don't want to look for 0 or +4, you're actually looking for negative 20. So just be aware of that. And we'll take a look over here. Let's see. We want to allow for 20 dB of headroom at the input circuit analog preamp to bring this to a nominal level. So what you're not seeing is this is the digital realm down here. So what we want to do is we want to increase this preamp gain until it's actually, we're adjusting the preamp gain. It's going through the digital, it's becoming digital, and then this meter is there. So it doesn't logically flow, but just know that as you turn the preamp gain up there. Now, you may find a need that after it's in the digital realm, you want to turn the digital volume down. 99% of the time, we just leave those digital gains where they're at. So, but the other thing is every single thing that comes into the system should be adjusted to where it's somewhere around -20. Now that's a little tough. You'll notice that it's a peak input level. So I look for, when I'm talking, my hard consonants and vowels should definitely be at like -16, 15, 18, something like that. But so kind of where I'm definitely getting above that -20 there. So. When we talk about microphone considerations, right? When we introduce microphones, ambient noise becomes something that's definitely that's going to be there because every room has noise in it, whether it's the HVAC, the building creaking, the network switch that's in the equipment rack and the credenza or isn't in a credenza, it's in an open rack and it's really adding to it, whatever the case may be. You need the signal level of each talker to be above the noise floor enough to ensure speech intelligibility. That was easy for me to say. But we want to go through, set all the microphones to -20 dB full scale. And then we want to go in and make sure that we have enough distance in here between the nominal level at -20 dB full scale and the ambient noise level at the mic, right? So AVIXA standard for speech intelligibility is 15 dB in a microphone. So if I'm at -20 and I need to have at least 15 dB of signal to noise ratio. So that tells me that from -20, I go -30, -35. So if I don't have a signal that's above -35, then I'm going to have issues. So if we look here at the nominal level, if I'm at -31, I only have 11 dB of signal to noise ratio between that input in there, and that's not going to work. So you're going to have to treat that on the outside. The way to test is to have a speaker start talking into a microphone, adjust the preamp level till it comes to -20 dB, have them stop talking. It's hard for me to do. And when that settles, you're going to see what that noise floor of that room is, right? And so if it's, in this case, it's -31.2, you don't have enough signal to noise ratio to have intelligent talking. So you would have to address that as the signal comes in or address the room, right? So what you're really looking for is, if you look in this example, is like a -43, something below -35 is going to do that. So once you have that, then you can start moving forward on that. So let's talk about microphone equalization. And here's another thing I just want to say. I just like control programming. Just DSP programming is also is like art, right? And every person is going to have their own way to do it. And what I'm giving you is just some best practices, some things that are industry standards. But there's going to be times and situations where you may do things that are off standard a little bit there. But the idea is, if I told everybody on this call to draw me a car, not everybody's drawing a 1972 Plymouth Valiant, right? If someone draws, a 1995 Honda Accord, that's still a car. It's not wrong, right? So that's the way I like for people to kind of approach it. And the same way with code. I mean, we probably got some control programmers out there too watching this. And how many people have opened up someone else's code and they're like, this guy doesn't know what he's doing, because they didn't code like you do or whatever. So it doesn't make sense to you. But so just remember that as we go through the audio, there's going to be some cases where you have to do something that's non-standard. But in a typical microphone signal path, you're going to bring the signal in, and typically you'll do a high pass filter. So we're going to just kind of cut off any of the low frequency stuff, especially in microphones, right? Typical cutoff frequency of 60 to 80 hertz. You could drag that up to 100. And we don't really care any type, any slope. That's kind of you can do a Butterworth, you can do whatever kind of choices you want to do in that. And then a lot of people will do a parametric EQ in between there in the low pass filter. And that parametric EQ, its job is we're going to go in and we're going to notch out little problematic frequencies. Now, microphone manufacturers typically will provide that like, hey, here's what we recommend you do to our mic to make it perform best. Plus, it's going to have effects on the room as well, too. So the low pass filter is just cutoff frequency based on your room factors and what that mic's going to do, right? Sometimes you can roll it off at different levels. We'll talk about that. But if you don't have 15 dB of signal noise ratio, you may be able to roll off some of the unwanted noise down on the low end and to address that signal noise. So there is some things we can do after that. Low pass around 16K, but you could go as low as 8K, and we'll talk about why that is. So the parametric EQ, like I said, you can consult the microphone manufacturer for your exact curves. You can use a separate EQ component for your mic EQ, and then one for your room EQ. So I would suggest if there's common things that the mic is going to deal with, you put them in the EQ with the microphone, and then you put a parametric EQ on the outbound side of your system that will address the common things in the room, right? Like, hey, I need to notch out this problem frequency that's reflecting a lot or something like that. Use separate EQ components for the mic and EQ. We just talked about that. Emphasize your speech frequencies if you need to. So a lot of people don't understand, the human voice goes from roughly 200 to about 8 to 10K up there. You can get down into 100. I haven't done a lot of Barry White's conference rooms, so I don't think that that's going to be a big problem. But typically, your vowels will fall between 250 and 1K or 1,000 hertz, right? So if you're losing that piece of it, you would want to accentuate or de-accentuate that. Your consonants are between 1,500 and 6,000 hertz. So that's where actually, just side note, if you're doing a sound masking system, typically that sound masking system should live somewhere in the 1,500 to 6,000, a blend of, and everybody has different methods. They like to do a blend of white and pink noise and this and that. But essentially, you're just trying to soften those hard consonants so that people can't understand what's being said. So now the last thing is the sibilance. And, for me, I'm old. I think of the Saturday Night Live skit where Tom Hanks and the Wayne's World guys are getting set up for Aerosmith to play their basement, and they're going sibilance, sibilance. But essentially, that's those S's, T's, and Z sounds. So that all happens at the higher part of the vocal range, up in 5 and 8. So I've actually saw this happen. I was working with a consultant on a project, and we were doing this really weird conference room, and he's like, "Give me something at a little bump at 7K," and I'm like, "What?" And all of a sudden, his vocal intelligibility just really popped out. So every room, everything's a little different, but the science behind it stands up to it. So now once you've done that, what you're going to want to do is you may want to use our notch feedback controller. Now, a lot of audio folks will be like, well, you don't need an automatic feedback eliminator if you know how to set up a room. And that's true. So you could use it as just a tool and then bypass it later. But that's going to give us some things. What we're going to do is we're going to bring in this notch feedback controller. We're going to set the fixed filter count to 0, the dynamic to 5, set our minimum frequency to 80, and set our maximum frequency to 20K. And we're going to find the thresholds where things are feeding back. So if I do that, it said here we want to set our fixed filters. So these are filters that the notch feedback controller is going to put in, and they will never get rid of them unless you hit clear all filters. So if you set that to 0 and set your dynamic to 4, what that's going to do is as it sees a feedback condition, it's going to drop in up to 4 filters to address that feedback situation. As you can see here, we have problem frequencies at 150 roughly, a little over 200, 210, and we have problem frequencies at about 600 and about 800. So that's what this is showing us, right? And so we're going to see these deep, and it's pulling out of there the threshold. We've set the feedback threshold at 40. So if the signals start to creep up to 40 dB, it starts notching down. You can see these notches are like 12 dB. So would we go over to our parametric and just start pulling that down? No, we wouldn't pull all the way down to 12 dB. We kind of approach it in a little more gentler manner. So what we do is so we're going to filter the frequencies in the parametric EQ block. We're going to start first with problem frequencies that are close together, like that 180 and the 210. Let's just put one little filter between that, kind of drag it down just a little bit. And you only want to apply enough attenuation to stop that feedback condition, right? That notch feedback controller is a oh crap button, right? It's like, Boom, I got to stop this right now. So it goes deep, it goes 12. You can see here that we've added like 6 dB, just little 6 dB bumps. Yeah, they're both at 6 dB. And a fairly not a huge amount of bandwidth. You don't want it too sharp because you want it to cover both of those problems. But the thing to remember also is manipulate the signal as little as you can. All of this fancy electronics does things to the phasing of the signal. It does things to the color of the signal and add things. So let's just nuance it down just a little bit. When the NFC no longer engages, go back to your notch feedback controller, it's downstream from your parametric, and you see where, okay, I'm not getting that feedback, boom. Now, one thing to remember, put one in, if, these do engage, the notch feedback controller engages level 2 memory usage, which is also AEC, also reserves that memory usage as well. So if you have 20 mics, don't put 20 notch feedback controllers in. Put it in your test tools or something like that, and just go through and use one to set up all your mics and then move forwards. All right, let me keep moving along here. So we have two different major types of mixers that we deal with. The first one would be a matrix mixer. We don't have a standard mixer, but essentially user assign what goes where. You can take inputs, route them to all the different outputs in any way, shape, or form you'd like to. Auto mixers are designed where we have no operator, right? Mics are going to be mixed to a mixed output. There's also options to have a direct output, right? So the automatic mixer is going to gate or gain share the different inputs, and then that's how they're going to come out of the outputs. Now, there's direct outs that are pre-gate and post-gate and all of that as well, but two major algorithms will decide which mic's output. Either will have a gain sharing or will have a gated one. The idea, though, is that mixed output is going to be a constant level regardless of how many mics are open, right? If I take a microphone at negative 20 dB full scale and I'm constantly talking into it and I add another one, if I'm doing that in a mixer, it's just going to keep mixing those signals and we're going to get a louder outcome. With the auto mixer, it maintains a constant output. Let's talk about each one of those just briefly. So most of you probably know how to use a standard matrix mixer. The cross-point controls adjust the relative level of each input. Now, one thing that does come up is people are like, why doesn't your mixer look like the rest of them? I think maybe just because we're a traditional audio company, we felt like, and also this goes all the way back to Media Matrix because our developers were the people that did Media Matrix. But so you've got your input faders here, you have your input trim gain up top, and then your outputs come out the side over here. So I know that in fixed architecture, a lot of open architecture DSPs kind of went along and formatted their mixers to where inputs come in the side and outputs go out the top. Just be aware in Q-SYS. And we get this question all the time. I mean, I teach a lot of classes and people are like, well, why didn't you just make it like everybody else's? I'm like, well, I don't know that we're going to spend time to reformat the visual properties of our mixer, but yeah, so just as long as you know the difference there, and usually these are all labeled, you can label these components as well too. Cross points are set. You can also go into the properties of a matrix mixer and you can add mute buttons if you want. But cross points set to 0 enables stuff to go through there. One of my key elements, and I say this is a generalized statement, but if someone sends me a conferencing file and they're like, I'm getting this problem, and I open their matrix mixer up and things are like -12, -13, 20, -28, +6. If that matrix mixer is all over the map and the cross points, then the problem is somewhere before there. Someone didn't set the input gain to everything to be uniform, right? That's why we set the input mics, the analog inputs coming in from, program audio sources, or heaven forbid, someone's still using a hard codec or something like that. So you have to make all of them be -20 dB full scale, because if you're trying to fix it in the mixer, it's going to be a mess. So just know that's a key indicator. If you're making a bunch of adjustments in here, you might. Typically what you'll see for me is my AEC output for my reference. I might, on the output side, if this is the output for the AEC, I might give it 3 to 6 dB of little bump of gain coming out of the mixer. But cross points are almost always hovering around 0. All right. Auto mixers used mostly for conferencing. Um, and speech reinforcement. They have adaptive threshold gating. The maximum number of open mics, or the NOM, is a suggested range between 1 and 3. And I love this because Matt Gray, one of our engineers, he says, if you have more than 3 people talking in a meeting, then you've got an argument. And really, how do you mic an argument, right? So even with you have a large room with a lot of microphones, I don't care if it's a 40-foot boardroom table with 30 mics on it, you still only really want about 3 mics open at one time. So that's just something to remember there. Your NOM attenuation settings. So some of this stuff, start with it at default. Go to the help file if you need to kind of dial in when you should adjust some of those. We're not going to dive super deep into setting up auto mixers, but just know that that's what that one's for. So what happens here in the NOM equation? And everyone usually points out, well, hey, Dan, you have it set to 4. We're going to just show you how the algorithm works, but typically we'll set it to no more than 3. So if you have just one mic that gates open, what it's going to do is it's going to give you, it's going to just let this negative 20 dB-ish signal level, dB full scale signal level come in, and you'll see that it's subtracting no gain. I love that we call this gain, but it's actually negative gain. It's pulling some subtracting signals out. One mic in, it's just going to let that pass through just fine. When we add a second microphone in, you'll know that when you add 2 signals of a kind of a similar or equal strength together, that it raises the output by 3 dB. So what we do is you'll notice that the algorithm will sense that 2 microphones are coming in, and they would be coming in around 24 or around -20. And then what you would see here is it'll start pulling about 3 dB out of that, because those 2 things, when they're summed together, are creating a little 3 dB bump. So we don't want that on the output side. We want the output of our mixer in our conferencing. It's going to be coming out, going to the far end of our conferencing, or into a room that I'm doing a presentation into. We want that level to remain constant. And then just for the sake of showing it, if we go down here to 4 mics open, that gain, that attenuation would come down to -6, right? So once we get to 4 mics, it'll do that. At 3, it's going to add 3 dB, maybe 4, but you kind of know that that's where it's at. That's what that mixer's doing for us. So the gain sharing auto mixer is based on the Dan Dugan algorithm. We don't pay for it, but it's based along those principles kind of around there. The gain sharing auto mixer works different from a gating auto mixer. There's a set amount of gain that it can hand out, right? And so what happens is the open mics will share that available gain. So if you look at this diagram here, all of these are sitting like everything is down -30 dB, right? And what's going to happen is as one microphone talks, we're going to grant more gain to that, see, right? So in this case right here, you'll see that 3 microphones are all gated open, right? In these 3 gate identifiers here. And what we've done is we've given them more ability. And what we're doing is this method of gain sharing between each microphone is a little different than gating, where we're letting a microphone pass, and then as mics sum together, inputs sum together, we're distracting the outside. That's kind of that's what the Dan Dugan does, or the gain sharing auto mixer does. Now, what I will say about that is, there we go. As the number of talkers grows, each mic gets granted. Works well for systems with a few mics. We recommend the gating auto mixer for anything over 8 to 12 microphones. In conferencing, I always use gating mic mixers. Gain sharing for me is when I have 8 less than 12 mics on maybe a dais or something like that, or I'm doing a town hall or a presentation space where I have a bunch of open mics, and those are open there, and as people are talking, the gain sharing works there. But when you get north of 12, and anytime you're in conferencing, I typically use gating. Once again, it's a preference thing, what you're comfortable with. All right, so let's put it all together. We often need to mix matrix mixers along with auto mixers in the same signal flow, and we allow adjustments before the auto mixer. Allowing adjustments before the auto mixer could affect the gating in the mic gating, right? So if you look at the gating mic mixer, nowhere in here do I have level adjustments, right? I'm not going to put gain adjustments before there. especially not ones that the user can see. So this block is user program level controls. Now you'll notice here that there's user controls for the gain going into the microphone and program mix that's going to go out to the loudspeakers in the room. And that's perfectly fine. What you'll see there though is some people will put, a gain out here that does one gain does it all. Some people will do independent gains on the program sources. That depends on how the system's designed, how your user is expecting it to do. And then on the input side, you'll see that the microphone inputs are calibrated to -20, just like dB full scale, just like the program inputs are. So let's talk about dynamic processing. Compressors will primarily level off loud talkers. By the way, we just did this last week. We only do it about every 6 months, but keep your eyes peeled for the deep dive that Steve McCary does for us on dynamic processing tools. He goes through in-depth how to use a compressor, how to use an AGC, how to use a limiter and things like that. And we're just going to touch on them in here, but there's a lot of good stuff. And you can also go out and find recordings of these webinars, probably just as good as me sitting here yammering in my office. So with that, compressors primarily level off the loud talkers. They can be aggressive sometimes for spoken word, less aggressive for vocal performance. And the idea I always like to tell people, you compress a vocal mic because you want to be able to feel when someone really gets into something. You'll feel the width of it, but it's just not going to clip and overdrive. And that's kind of how compressors work. AGC helps for quiet talkers. You need to be, pretty efficient with how you use it. And it will help for loud talkers. Now, there's some guidelines in there. I think somewhere in 4 to 6 dB is about all of the amount of swing of gain that you want to add or subtract. You start getting outside of that realm and they'll run away with themselves because they'll be like, oh, it's not loud enough, and it'll keep turning up too much. And it works slower than a compressor. And if not set up, it will continue to raise its level based on noise that's in the room. So those are some things to think about there. What's wrong with this picture? I always say it's like trying to pay my Visa with a MasterCard, right? So you don't ever want to put gates in front of a gating automic mixer. I should have given myself this webinar 20 years ago when I had a noisy mic in a conference room that had noise being induced from the conduit run that was run. I think the mic was run to the table, either in the same conduit as the power or next to it. And I put a gate in it before the gating mic mixer, and you don't want to be gating something. The gating mic mixer needs to get a raw signal applied to it. So introducing AEC to your system. Now this becomes another whole challenge there. We may have a lot of folks here that have done conferencing. Maybe we have some that haven't. So I'm going to kind of talk about this in general terms, assuming that you don't have a lot of conferencing experience. And we're going to talk mostly about primary things to watch out for on there. So conferencing tech terminology. So latency. It takes a little bit of time for the, what is AEC in anyways? Well, AEC is where we take the signal that's coming out of the loudspeakers in the room, right? Because we have a microphone, and microphones, even condenser mics with phantom power and things like that, they're dumb. When sound waves hit them, they amplify that sound wave. And they don't know if that sound wave is my voice in the conference room or if it's the voices or the stuff coming out of the loudspeaker above you, right? So that's what the AEC does for us. So we provide to the AEC a reference, and we say, hey, based on this reference, whatever you hear coming in from the microphone, subtract that out. And the only thing that we want to leave the acoustic echo canceller is just the microphone audio that's coming in that isn't the loudspeaker audio. So when you build your reference, that's what you're looking for. But it takes a while to do this, right? So we need some look ahead time. So if you're doing from the input of the AC to just the conferencing output, there's about 32 milliseconds on the Core 8 Flex. I just had marketing redo this. Go to the help file and double check this, because I feel like those numbers are backwards, but I could be wrong. So I feel like it's 32 milliseconds for when you go through the reinforcement. No, I think this is right, because the reinforcement outputs actually have they're everything except the last nonlinear piece of processing. So anyways, it takes about 32 milliseconds for input to conference output. And all other cores other than the small form factors listed there are 26.7. So you get in that Core 10X, you get into, if you still have a Core 510, a 610, those bigger processors can process these signals faster. So, and we'll talk about what the reinforcement output is if you're not familiar with that. Tail length. This is another thing to understand. This is a huge differentiator in the Q-SYS platform. Tail length, the industry standard for the tail length of an AEC algorithm is, and tail length is how long it listens to the room before it does its subtractive process, right? And so we have the ability in Q-SYS, 200 milliseconds is kind of the industry standard, but we have the ability in Q-SYS, we have a software-based AEC. We can set that at 100 milliseconds. Don't recommend that unless the room is really well acoustically treated. There's not a lot of reflections. You've got microphones right at people's mouths, things like that. 200 is what they're set to default at, but we have the ability to go to 300 and 400 millisecond options for when you have really reflective spaces or really large cavernous spaces. And that's huge. That's actually, there was some time several years ago where Ford Motor Company was trying to do a new executive boardroom, and imagine this, AV folks, the architect won out, and the form, function, and the looks of the boardroom were more important than the acoustics of the boardroom, right? You know, concave hard deck ceiling, marble table, glass walls, and they're like, it sounds like a speakerphone. We want it to say, you know. And so in that big reflective space that they weren't willing to do acoustic treatment, other competitors, DSPs, could not produce what they considered a satisfactory phone call. We brought Q-SYS in. Then we were able to set those to, I think, 300 or 400 milliseconds. So it was able to deal with a lot more of that reflections that were coming in. And we ended up winning the business. It took about 2 years, and we became the standard in Ford Motor Company's global conferencing platform. So, you know, it can win you business, right? So typically design your systems around 200 unless you know that it's going to be a really reflective space. And we'll talk about what that costs too. You know, we sell a Core 110, and I'm going to have to switch this to, you know, we sell a Core 110 and we say it has 16 channels of AEC. That's at 200 milliseconds. When you go to 300, it eats up more memory. It's going to be, you're going to go from 16 to 12. And if you need to go all the way to 400 milliseconds, you're going to go from 16 to 8 channels of AEC. So you have to think about that. Now, we might have some salespeople on here. If you go from, take a Core 110 to 100 milliseconds, you would get 24 channels of AEC. But don't be like, you know, oh, I'll design for 24 unless you absolutely know those rooms are acoustically treated right. So reference to microphone level, you'll see this mentioned. It's the difference in level between the reference signal that's coming in and the resulting signal at the microphone, right? So if we look at the it's also known as echo return loss in non-QSC DSPs. So, you know, this person on the far end is talking, it's coming out of the loudspeaker. We're providing a reference of that signal into the adaptive algorithm. The microphone hears what that speech coming back, and it subtracts it out so that when you go back to the far end, that you know that you're not getting it. It's the difference that we are pulling that out. Residual echo suppression would be the same thing as in other platforms are called nonlinear processing. It just essentially removes the error signal after the AEC does what it needs to do. Voice lift in larger rooms where the near-end microphones are being sent to the far end, where near-end microphones are being sent to the near end as well. So voice lift and mix minus are two different strategies. Voice lift, I'll give the example of, I'm doing a training room and the instructor is 99% of the time at the front of the room and they may have a lavalier mic on. And voice lift is, I'm going to go to the back row of loudspeakers. You know, maybe they're 30 feet away. My voice really is only carrying a good 15 feet. So 15, 20 feet back in the room, I may have a row of loudspeakers that I'm going to lift just enough of my voice, not so that it sounds like Sunday, Sunday at the monster truck rally. It should just feel natural. And, you know, sometimes you have to argue with your customers. You have to explain to them. They're like, well, I don't hear it back here. And it's like, no, it should just feel really natural when it comes out of there. So it doesn't need to be, you know, some people will be like, I don't think that the mic's working because I don't hear myself in the room. And if I'm 20 feet away from the loudspeakers, the people under it should hear my voice naturally. And the person at the front of the room shouldn't hear their voice. So I could do a 2 hour thing just on voice lift. Mix minus is where you have distinct speakerphones. Let's say of a long boardroom table. We got 20 people at a boardroom table, 30 people, 15 to people on each side. The people at the far end are going to end up being 15, 20, 30 feet away from the people at the other end. So what you do is you plant loudspeakers in the ceiling and on independent channels. And if I'm at the head of the table and I talk into my mic, it's going to come out, the loudspeakers closest to me, it's going to come out 12, none. The next row of loudspeakers down, it might be 12 dB down. The next row of loudspeakers, it'll be only 9 dB, and then the next one might be 3. Being that, depending on where I'm at, I'm going to mix that. Now, that also means each microphone is going to need its own reference built based on the other microphones that are being lifted to that. So, path to the far end. So this is a basic conferencing signal flow. You have local microphones coming in. They go into the acoustic canceller. We go through a gating mic mixer, and then we go out the VoIP out. You could be going analog out to a conferencing hard codec. This could be USB conferencing out, whatever the case is, right? And then the path to the near end is you bring, whatever program audio in the room is coming in, and you bring the VoIP, the USB, the whatever it is, the far end audio comes in. You mix that together, and then you push that out the loudspeakers. Now, this right here is everything that's going to the loudspeakers is the reference. Now, typically, some people will do 2 mixers and they'll bring things in and just go to the loudspeaker and they'll build a separate mix down here, especially if they have multiple conference types or something like that. But the idea is whatever's the rule of thumb here, whatever's going to the loudspeakers, if you're not lifting mics in the room, goes to the reference there. Typically, apply equalization, compression, automatic gain consistency for level. Best practices are to do all of that after the AEC algorithm. So this is don't do what I show here. Never put dynamics ahead of the AEC. So if you had, there was a time, so these dynamics typically should be moved over to the other side here. So this is not what to do. Never put them ahead of the AEC. No nonlinear objects especially. So I've seen some people, when the beamforming ceiling mics first started coming out and before they had kind of a low pass built into them or a high pass filter built into them, we would see people before the acoustic echo canceller add a high pass filter and just to roll everything off below 80 hertz, because those early algorithms running the beamforming mics would pick up a lot of low end resolution in the rooms, but they've kind of addressed that now. So the AEC reference, the most important factor in successful AEC is having the correct reference signal. So whatever goes to the loudspeakers in the room goes to the reference. All of the far end audio coming in that's coming out of the loudspeakers, any program sources, especially program sources, should go into the reference if you're sending them to the far end. Never put a microphone into its own signal reference. If you do that, it'll be really easy to tell. The people on the far end are going to go, it sounds like you're underwater, because it's really going to try to get rid of its own signal there. And so it's going to have a real underwater sound. Assuming you've already brought in all your microphones, signals to -20 dB full scale, and you're achieving at least 15 dB of intelligibility, we're going to have to lean back to 24 or 45, 50 minutes ago and lean into this, right? So if we've set our gain structure up right, set your amplifiers to a minimum level or set your output block max RMS gain to -40 dBu if there's no controls on the amp. And then use your preamp analog gain to bring all program sources to -20 full scale, and then leave your program sources at unity gain throughout. So with a calibrated program source, you're going to bring something in into the system. You're going to set the room to output about -70 dB SPL. And you know what? I have a free app on my phone. I think it's called DB meter or something like that. Set that down in the middle of the conference room and just bring the gain of this calibrated source. Voice isn't the best. Find music and just, a consistent, easy, or a good speech track that you can play, something like that. And you just want that DB meter to be hovering around 70. I'll tell you why 70. The average human voice talking across the table is about 65 dB. And so I used to always think, well, I'm going to set my conference rooms up at -65 because that's what people like to hear. And I've noticed that every time someone used my conference system, they'd get on the call, the other people would start talking, and they'd go tap, tap. And they would bring it up, 3 dB steps, they bring it up about 6 dB to 70, 71 dB. And it's because humans in a conference environment want that audio that's coming back at them just a little bit louder than normal human speech, right? It's just a thing that people want to hear. So -70 is what you want that system to be outputting at. Then you're just going to make a test call. You're going to adjust the far end gains level to the nominal receive level, right? So the VoIP coming in, make sure it's at -20 dB full scale. With the listener at the far end, the AEC can then be fine-tuned. So you want someone listening on the other end of the call, and then that's how you're going to start fine-tuning it. Noise reduction enable. So if you turn that on, you're going to be able to reduce noise in the room. Now, it's only going to reduce steady state noise. It's that's going to be the fan that's blowing on there. But if somebody drops a plate of dishes in the cafeteria outside the conference room, that's not going to get rid of that. Bob the loud talker, with his voice talking up and down, that's not a steady state in the conference room next to you. That's not going to get rid of that. So it's just going to be those things like that. Also, the more you use, the more it's going to color that signal. So, it's important that you choose the correct conference rooms when possible to do it based on noise and things like that. So let's walk around the AEC block a little bit more. The RMLR, this is the easiest meter in Q-SYS to use. And what this is looking for is it's the reference to microphone level, right? So if you're providing too much reference to the algorithm, that is going to go from green in the middle, that bar is going to go up and go yellow, orange, and red. If you don't have enough, it's going to go yellow, orange, red down. So when you're talking, what you're going to do is get on a call, have the far end talk into the room. And when they're talking, that should be hovering right around that green area there. So if you have multiple microphones in the design, set it so that you'll increase in one AEC, a shared AEC gain reference. You'll bring that gain in, and then you'll use these reference gains below it to adjust so that they're all right at that 0 level or that mid level there. The adaptive filter up top, I'll talk about this briefly. This is only used if for some reason you don't have the ability to mute your mics after the AEC algorithm. Let's say for some reason you have microphones that have mute buttons on them and they have no programmatic control, and the only way you can give a mute button to people at the table is they actually mute the mic. What you're going to do, the echo canceller wants to be listening to the room all the time so that it doesn't have to reconverge and figure out what the noise is. If you completely mute the audio, it loses the noise floor, it loses everything. What this adaptive filter does is you open up all the mics in the room and you're just quiet. And what you're going to see, you're going to look at the mic input meters. You're going to see where that noise floor is. So if that noise floor is around -48 dB, you're going to go over to the adaptive filter and you're going to start around -48, -50. And what that does is, hey, if this mic gets muted, I'm going to kind of assume that last noise floor I heard around -50, it's going to hold that level. And then when the mic opens back up, it's going to converge faster and start doing that subtractive process. So noise, if the noise floor is like -60, set it to about -65. So within a few dB there. Anyways, that's what that is. RMLR enable level. This sets the nonlinear processing over here. So the residual echo suppression, it should be the RES. Increase the RES to handle that right there. This sets the nonlinear processing. Increase if there's residual echo, but at some point, if you turn this up too much, the residual echo suppression, you're going to end up with getting to a half duplex. So it's going to be like a walkie-talkie instead of a phone call, right? So just make sure that you're not turning that up too much, but that will help. Essentially, I like to look at that like, hey, it's kind of like adding a little bit of tail length to the 200 or the 300 that I'm set to. What if you still have significant echo and you've done all of this stuff? Well, make sure that your signals aren't misrouted or looped. This can especially happen with old-fashioned, with the video codecs. A lot of times they would push a signal back, right? Because they'll have a reinforcement output and it's already got everything subtracted. Then you can go through, but you can mute microphones to verify that it's really echo and you're not just direct coupling a microphone back into the signal. If the echo is still there, then mute all of your inputs and then start mute each input one at a time until you identify which source you might have wrist routed. And you'll see if it's a really significant echo, you'll know that it's happening. What if there's still echo? Check your tail length. If it's at 100, go to 200. If it's at 200, don't automatically just jump to 300 or 400. Only large reflective rooms are going to require that. You may have to recommend methods to reduce reflectivity of the room, right? There's artwork that looks like that, or there's artwork, or I'm sorry, there's acoustic treatment that can look like artwork. There's, you know, there's a lot of things you can do. So, or just tell people that they need to make their conference room an anechoic chamber like that. So, all right. So what we're going to do is we're going to go in and set our conferencing setup. We're going to repeat our step 4 here. Finally, the last, we'll go through, did I miss a slide in here? All right. Well, sometimes you find them. So what you're going to do once you've set all of that stuff up is the last step is this, is that you want to finally make a test call. Once we have the gain set up on each of the POTS calls, we do still have plain old telephone. If you want to, we have, you can buy QIO boxes with a analog line in, video codec, USB conferencing, whatever it is. Set up a test call with all of your conferencing types, right? And that's the important thing to do. A lot of times people, I know I used to be guilty of, well, the worst signal in the whole thing is the analog phone line coming in. So if I make that sound good, everything will sound good. But you know, if you have multiple conferencing types, VoIP and USB and then system design, get a call coming in USB, get a call coming in VoIP, make sure that they're hearing each other properly and that your levels are not mixing. So that's the last step you want to do. Now, once we get after the mixer, typical design elements we'll see after the mixer is going to be some equalization, where you may see some user level controls at that point. We're going to see limiting and we may see delay, right? That's typical things that we'd see. So post-mix EQ, the EQ in the signal chain is typically for a speaker or a room EQ, right? So some loudspeakers are going to say, you know, hey, the manufacturer says, if you use, you know, this loudspeaker, it has a, you know, you need to notch down the 2K frequency and the 4.2 or whatever. There may be things to make it flat. Now, when we say flat in the speaker world, we mean that whatever waveform is put in it, it accurately as possible reproduces that. So if a speaker has something in its design that makes it have a bump at 2K or a dip at 2K, then you're gonna, you know, you're gonna put a signal in, and when you get to 2K, it's going to adversely affect that. So you want to make it flat, and you know, sometimes they may recommend adding a bump here or a subtraction there. It counts for imperfections in the frequency speaker. Now in QSC speakers, when you're using analog amps, we have intrinsic correction blocks for each one of our loudspeakers. So it's just an FIR filter that goes in there and knows what to do. You can put that in line if you're using an analog amp. If you're using one of our digital amps, you add that to the outboard side of the digital amplifier in your Q-SYS design file. And it's going to say, oh, that loudspeaker's 70 volt. And it's going to go back and configure the output for 70 volt, or it's low impedance. It's going to configure that. It's going to say, oh, that's a such and such type of speaker. So it only can handle this much wattage, this much, you know, it knows what the limits are. So a lot of that gets taken care of in there. The other thing that the EQ signal output chain is the room EQ, right? So we were talking about earlier, like, if I have all of the same conference mics that are, or mics that are being, podium mics that are being lifted into a space or something, I may put some little bit of feedback elimination there. But really, if every mic is going to be challenged by the same dip at, let's just say at 200 hertz and at 700 hertz, like we had in our example, I could probably, instead of having those little notches and 6 different parametrics on the front end, I could just notch out 3 or 6 dB on the outboard side for the mics. Now, if that becomes too large, you may want to keep it at the mics because you don't want the program audio to be missing those notches. It's just going to depend, but that's what you could see. User gain controls. Our user gains better at the input or the output side of the mixer. Don't do both. Okay, so too many user control gain controls will negatively impact your gain structure. So you don't want to give people the ability to adjust volume level prior to mixing the signal and then afterwards too, because they're going to turn one down and then crank one up or whatever the case may be. Does the user need to control the level of all the outputs pre-mixer, or do they need to control just one for the room? 99% of the time, basic systems, conference rooms, things like that, people are not audio engineers, right? They just want to make the sound coming out of the loudspeakers louder, whether that's the conference or the TV or whatever the case may be. But use your discretion. I also don't give them enough to ruin the entire gain structure, right? So user control to ruin the gain structure. Set reasonable upper and lower limits on your gain. Now, in all the Q-SYS gain blocks, you can set a max gain and a minimum gain. By default, they will go to 20 plus 20 dB down to negative 100. I like to do negative 40 because if people turn on the negative 40, they can still barely hear it, and then they don't blame the system for not working. They're like, oh, I need to turn up the volume or my lap, you know. Some people do 0 to negative 60. Just depends on what you want to do there. So output limiting. So limiting prevents a signal from going. Typically, you see compressors and AGC on the front end signals, and you'll see limiters and peak limiters on the output port. Limiting prevents a signal from going beyond a predetermined level. It prevents that signal from clipping, and it prevents overloading amplifier channels. A peak limiter block, default threshold is 0 dB, but let's take a look at what's ideal. So when we look at a limiting situation, as the input signal is being, when it's below the threshold here, it's not being affected, right? So when we set our limit here at 0, right? Like, hey, we don't want it to go above 0 dB in here. What we could do, the clipping point, is you'll notice that if I set the limiter at 0, it's still going to overshoot it by about 6 dB, and then it takes a little bit of time for that to react. So what we typically like to do, the limiter takes effect, but it shoots beyond that threshold. What we want to do is we want to go in and we want to set that limit at, whoa, I didn't say you could do that. We want to set that limit at like -3 here so that, maybe it shoots up and it doesn't quite overshoot as bad. You may want to set it to -6 just to keep that control over there. And the whole idea here is in the digital world, we want to be applying, -3 to right around 0. And that's going to give us a full scale, plus 24 dBu is when it's going to go out there. So that's what we're going to be doing there. And then amplifier limiting. So if you do your limiting on the outboard side, QSC limiters are set automatically if the speaker box are correctly configured. There's a few types of limiting that we do in here. We have an AC limit, which is a clipping stage before the amplifier. So before it goes into the input of the amplifier, the DAC limit there would go into the digital analog converter. And then you've got protect, which would limit driving to low impedance conditions. So if you have a shorted wire condition, right, it's going to limit that output and say, or if it's driving into just 0 impedance or very low impedance is 2 wires shorted together. And then, 4 ohms is whatever the coil of a speaker, or 6 or 8. Limit is computed limiting based on a load type. So just depending on what that is. So you'll set different limits in there with the digital amplifiers. Output gain structure. If you're not going to a QSC amplifier, shame on you, buy QSC amplifiers. So you'll ultimately want to convert the digital audio back to analog. In this limiting example, we saw clipping at 0 dB full scale, as you would expect. In keeping with -20 dB full scale gain structure, the digital gain should be left at 0, okay? And then what happens is at 0 dB digital gain, the RMS output level when the analog is at gain. So this is perfect for standard downstream devices that are professional level, right? I'm coming out of this, I'm going into a mixer, I'm going into a professional recording device, I'm going into whatever. And so it's expecting to clip at plus 24 dBu. What if the next line down is consumer level, right? Well, then what we got to do there is it's looking for consumer line level is about -8 dBu, right? So here's the digital world, it goes to the analog converter, and then it comes out of the design. So in order to not clip that, we want to make sure that when we're at, essentially full 0 dB full scale, that we're only outputting about -8 dBu, right? So that we're not clipping that. But yet we're keeping our gain structure consistent all the way through. We're going to assume 12 dB of headroom and assume the maximum input level of plus 4 dBu RMS, right? So now we reach 7 dBu peaks when we're at 0 dB full scale. So we're just a little under there. That's now calibrated to there. Sometimes there might be a case when you've got to feed a microphone level device. Make sure that device doesn't provide phantom power back. It's going to mess with the output. It's going to damage the output circuit of the Q-SYS output circuit. But cut that RMS level back down to -40 dBu. So essentially you would come down here and you would turn this all the way down. So you're going to have a max RMS of -40 out to reach that mic level. Output gain structure. So decreasing the output level, as you can see here, right? If we go from professional line level to consumer line level to microphone level, you can see that the signal to noise ratio, if I wanted my button to do that, it wouldn't do it. You see that it goes from the professional line level here. You have a lot of signal to noise ratio. Let's just say this is at, -80 dBu. So we've got 104 dB of headroom. Here we only end up with, if we go negative to 10 down, now you've got almost 70, -70. And then here you've got, -40. So you just don't have as much signal to noise ratio, right? So you just want to use professional line level whenever possible. So I'm just going to do a quick wrap up here. Input calibration, adjust analog gain to bring all of your Q-SYS inputs into the system at -20 dB full scale. All inputs, microphone, program, conference alike. Microphone EQ, trim the high and the low frequency noise with low pass and high pass filters. Parametric EQ should be used to put manufacturer suggested curves in there for the mic. And then use notch filter or parametric EQ to trim out any problematic feedback frequencies. And then you can use a notch feedback controller to identify what those are. If you don't have, any test equipment in the room to do that, use what's built into Q-SYS. Microphone dynamics, so automatic gain controller compressors can be used to get consistent levels from your wide range of talkers. Remember, we don't put those ahead of the AEC most of the time. They go after that. And then auto mixing. Do not place user controls or gates ahead of the auto mixers. Use gating auto mixers for noisy rooms or rooms with more than 8 or 12, or for conferencing if you're Dan. Use the fewest number of gain controls to get the pod done, right? Sometimes even in your own design, if you've got too many places to adjust gain, you'll forget that you made a bump over here and now you're wondering why it's manipulating incorrectly further downstream. So it's just good to have that. Use the fewest gain controls possible to get the job done. Avoid multiple gain controls. Avoid adjust ranges to keep the users from ruining the gain structure too. Output limiting. QSC amplifiers limit automatically when intrinsic correction and generic speaker blocks are set up correctly. Use the peak limiter component to protect outputs from clipping. With a for the proper normal gain structure, -3 dB full scale is a good limiter threshold. Output calibration, use the analog output gain setting to adjust the max output level. All right, so there is a follow-up quiz if you go to qsc.com/gain structure, and you'll get this with your thing there as well. Plus, you'll get a copy of this troubleshooting guide. Will get sent out with this as well. You can go and get half of an Avixa credit for attending this. So please do that if you would like to. And with that, I will say thank you. Any questions for me? Oh, James Cargill saying hello from U of M. So, all right. You were in last week's dynamic audio processing. So, all right. I ran just a little bit long, but I appreciate everyone hanging in there with me. So if you don't have any questions, please feel free to download the recording, use it as necessary. Hopefully that you've gleaned something from this as well. And I will, if you give me just a quick second, I'll give you a quick brief on what else to expect down the road here. So let me just look. Next week, I believe, is it next week or the week after? We've got a deep dive on the new line of Q-SYS processors. So that's going to be interesting for everybody. So just kind of talking about what the Core 24, the X10, the X20, like where their best use cases are going to be. So yeah, so March 10th, that's going to be how to choose the right core processor. And then March 24th, we have part 2 of Skip Mussett, our trainer down in Austin. He's doing UCI tools, advanced CSS techniques. So in his first one, he talked about kind of some common things about when you build a CSS sheet, cascading style sheet. And then in this one, he talks about some advanced techniques for us. If we've got people out there that are doing CSS with HTML and are deep divers in it, you'll know that Q-SYS looks at the CSS file and then replicates the certain things of it. But we also render our UCIs for web application, for the Apple app, and for our touch panels as well. So, not every single CSS characteristic comes through. And then this one is important. If you're not familiar with our new Room Suite, it's essentially is a small form factor systems that you can go in and you configure them. Hey, I added this Q-SYS mic, or I added this beamforming mic, this pieces, and it will write the code. It'll do the touch panel file for you. That Angela's going to be doing, Angela Brown from our distribution team, the application engineer, she's going to be doing the Room Suite design. That's obviously a product for that small room, that medium room, definitely for our people that are doing distribution and buying through distribution. It's a great place there. James says, what are your best practices for noise reduction when the output will be going into Zoom? So when we're going into Zoom or any USB, the default Zoom settings on our medical campus include noise removal, auto echo cancellation. I would say in that case, if this was 10 years ago, James, I would say the DSP is going to do it better. But I will tell you, and I have more experience with Teams than I do Zoom, but Zoom, I think, is the same way. The noise removal and things like that in the newer conferencing devices and the soft conferencing is doing a great job. So I would start without that. And then if you're finding that you're still getting a little bit of noise, then go back into the echo canceller and do some of that in there. Kind of experiment with what works best for you there in that case. Like I said, 10 years ago, the algorithms in the soft conferencing and in the codecs and things like that just couldn't handle it. Now, I mean, it was crazy. I was in New York City and working at our New York Experience Center we're building, and I'm walking home talking to my wife on the phone, and literally a ambulance or a fire truck stopped at the stoplight right by me or was driving by me. She didn't hear it at all. It's like, man, the algorithm on cell phones has gone crazy. So any specific tweaks that you would do for Teams versus Zooms? Teams normally sounds worse in my experience. I haven't done a lot of conferencing setups in the last few months or last few years since I've kind of moved into a management role. I'm not dealing with those a lot. But what I would suggest, James, is if you're at the University of Michigan, reach out to Jonathan Moore is one of the point of contacts. It's an engineer that supports that arm of our business, or even your regional guys. So there's guys in the Northeast region, application engineers, would be Eric Marchitelli and all of that. Or if you just want to drop me an email, I can connect you with those guys, and they'd be happy to connect with you and talk. I believe in don't BS someone if you haven't had that experience deep in it recently, only because those things change. They've gotten so much better and dynamic there. So any other questions? James says, thanks for the fantastic class. Absolutely. I appreciate it. Sometimes it's funny. We set this up and, we get people that attend. I could run this one every month and there would be at least 30 or 40 people in it. And even people that, that do a lot of DSP work. And I think one of the things in our business, and I just see this going back to like, if you have most people, You don't have to be a crazy programmer to make audio come into a box and go out. But that doesn't make you an audio person or a DSP person, right? And I think that's a disservice that our business has done. And typically most integration offices or whatever will have one or two people that are really good DSP and the other people that can make audio go through a DSP and come out. And so that's why we have the deep dives so that people learn more. I love to see people out there supporting the other people. I always say, if you don't train the person below you to take your job, then you're never going to be able to move up. So anyways, this is going to turn into thoughts from an old guy here. So, but anyways, thank you all very much. I appreciate you going a little over time with me, and have a great week. And hopefully we'll see you in March for some of those deep dives. Thank you.